Hello, welcome everybody, and thank you for joining us today. My name is Pavel Rudko, and I'm a senior software engineer working in the developer advocacy team at ARM. My main background is mobile graphics and mobile machine learning, and today I'm looking into machine learning in gaming and graphics. And today we will be talking to you about mobile machine learning in gaming. So we will cover such topics as ML use cases in gaming, different ML frameworks for mobile, the process of preparing a neural network model for mobile, and hardware compute units, as well as different ML and graphic pipeline optimizations that you can apply to your project. And also we will cover data transfer and synchronization. The reason machine learning is so popular is because it allows you to solve the problems that cannot be coded in the usual way. Neural networks are trained on real-world data and provide realistic results. It can be useful in many different areas, and gameplay process is one of the areas in which it is highly beneficial. When it comes to AI, then realistic human behavior can provide really nice user experience. If we deal, for example, with AI-based teammates or enemies, then the players can really appreciate realistic behavior. And when it comes to multiplayer games, we can even copy the style of a world-famous player, providing a unique experience of being his teammate or his enemy. Another area in which ML can be very beneficial is graphics. It can be different image quality improvements using denoising or supersampling, and style transfer can also allow us to implement complex post-processing effects which cannot be done just by using shaders. But these use cases are at the early stage of development. We can expect it to become a trend in the future. However, today we would like to focus on another very important use case, which is especially popular on mobile, and it is AR. So in order to combine a game with the real world, we need to get certain data from the environment. And in this case, neural networks help us to solve such tasks as depth prediction, body pose tracking and gesture recognition, face features recognition, and also background segmentation. For using ML in all these cases, we need a way to perform neural network inference. That means executing the neural network on the target device. And there is a number of machine learning frameworks which make it possible. When it comes to the choice of ML framework for your project, there are certain key points to pay attention to. The most obvious are performance and ease of use. High-level frameworks make it easier to get things running, but native options such as CoreML, for example, can provide better speed. Also, sometimes with different ML frameworks, the desired model support can be an issue if the framework, for example, lacks support of certain operation types or adds restrictions on certain layer settings such as padding, strides, or dilations. In this case, the developer probably needs to do a reverse engineering of the neural network model, which can be tedious, and sometimes it leads to worse accuracy or performance. And integration with a game engine is another beneficial feature, because if there is already an existing plugin which allows you to use an ML framework in your game engine of choice, then you won't need to spend time on writing your own. The last point to mention is device support. And although most of the frameworks cover a wide range of devices, sometimes the developers can expect some restrictions. So let's take a look at the existing options. The most popular ones are TensorFlow Lite and PyTorch Mobile. They provide inference both on Android and iOS. And on Android, we also have ARMNN. ARMNN is a highly optimized neural inference engine which delivers best performance on ARM GPUs and CPUs. It can be used by the application developers directly or can be enabled as a TF-Lite delegate. But Unity has taken another approach. They have created their own mobile inference framework, which is called Barracuda, and it can be easily installed in Unity as any other asset used in Package Manager. It provides a GPU backend which relies on compute shaders and also a very fast CPU backend which uses Unity Burst technology. But to get the best inference on ARM-based GPUs and CPUs, the best option is to use ARMNN, and I would like to share my own experience using ARMNN together with Unity. We wanted to showcase how to use different hardware components such as CPU and GPU together for graphics and ML at the same time. And NAR Filterup is a great example, but at the same time very challenging because we need to deal with real-time neural network inference. And we process the continuous stream of frames from the camera. In this app, the user can be put into a virtual environment by replacing the background or attaching a 3D object to his head. And in order to do that, each frame we execute 3 neural networks for background separation, face detection, and face landmarks recognition. In order to combine 2 technologies, ARMNN and Unity, we have created a simple C++ plugin which serves as a bridge. So let's have a look at the ways to achieve real-time neural network inference because it wasn't straightforward. With real-time processing, performance becomes particularly important, and we need to look for any opportunity to save an extra millisecond per frame. The best way to speed up the workload is, of course, to reduce the number of computations. So first, let's take a look at the neural network models themselves. The model is defined by its architecture. That means input and output shapes, set of neural layers and connections between these layers. And once we define the structure of the neural network, we can train it on a data set. That means a large set of input examples and corresponding example outputs that we expect from the neural network. Normally, when dealing with images, the most popular type of the architecture is encoder-decoder architectures. So in this case, encoder extracts the features from the image, and these features can then be interpreted differently by the decoder depending on the task. For example, you can see on this diagram, a classifier can tell us if we see a person or a cat on the image. And if our use case is upsampling, then the decoder produces another image, for example, a grayscale mask of a person. When it comes to such architectures, then using an existing pre-trained encoder can be very beneficial because it is already well optimized, and it can also save you a lot of time during the training process because you only need to train the decoder part for your task. Also, it is worth trying to experiment with the number of layers in the encoder, which is known as depth multiplier. And it can allow you to achieve good compromise between accuracy and the number of operations. But you can also make the operations themselves lighter by, for example, reducing the number of output features in the convolutional layers. But how can we compare different neural networks in terms of complexity and pick the better one? The most important metrics in this case are millions of operations, millions of multiply accumulates, and the total number of parameters in the neural network. Normally, the convolutional layers are the heaviest, and if we know the number of convolutional layers and their settings, such as paddings, strides, or dilations, then we can estimate the total number of multiplications that are required by these layers, as you can see on this diagram. But there is also one additional step that we can perform to achieve better performance, reduce memory footprint, and power consumption. It is very important on mobile because we don't want to drain the battery very fast. And this additional step is called pruning. That means getting rid of insignificant weights, in this case it is called weight pruning, or getting rid of insignificant connections between the layers, and it is called structured pruning. If you want to know more about this topic, then you can check out the link that we will share in the end of this presentation. Let's have a look now at different compute units that can be used for neural network inference. GPU is really great for inference because it allows us to perform computations in parallel. Tensors in GPUs can be represented as textures or buffers, and single GPU core can launch hundreds of threads at the same time. And this scales very well. The more cores we have, the more threads we can launch. Also, often if we deal with ML on GPU and we have graphics on GPU, then data transition can be performed in the most efficient way. However, it is important to keep in mind that GPU can be already busy with another workload, for example, graphics, and two workloads can negatively impact each other. So let's have a look at other options. CPU. Although CPU is based on sequential model execution, we can still use multithreading and SIMD instructions to speed up the inference. It also aligns very well with image processing because we can multiply few input values by few weight values at the same time. One of the backends in Unity Barracuda, for example, uses their burst technology, which utilizes SIMD functionality. And in ARMNN, one of the backends uses ARM Neon technology, which is also SIMD. In some cases, when we are doing GPU inference and some operators are not supported, they will fall back to CPU execution. And these CPU-GPU switches can be costly, so it's better to evaluate if it's worth trying to perform the entire model on CPU. NPU is another alternative. Their hardware is specifically designed for executing ML workloads. And as the set of operations is implemented by the hardware, we have a compromise between speed and flexibility. NPUs are also very efficient in terms of power consumption. Unfortunately, not all the modern mobile phones come with an NPU, and even the existing NPUs are not very easy and straightforward to program because we normally rely on third-party or we normally rely on vendor-specific libraries and SDKs, but we expect the situation to become better in the future. NPUs also normally support only quantized neural networks. That means that all the data in these networks is represented by integer numbers. But making sure NN inference is fast is not enough. When it comes to a complex application such as game, then the entire pipeline needs to be optimized. We would like to share some tips for improving performance when ML and graphics are used together. One thing to consider is using different compute units to execute different workloads at the same time. For example, if there are two neural networks, then one of them can be executed on a CPU and another one can be executed on a GPU. Or if, for example, we have only one neural network, then we can execute it on a CPU and GPU will be busy with graphics and it will be run in parallel. AR is a set of concurrent tasks and it can be, for example, neural network inference, image processing, and graphics, and making sure that the entire system on chip works together very well, like GPU together with CPU, is very important. Another important point to consider is the way pre- and post-processing is done. Input pre-processing is normally required when dealing with images. It can be, for example, cropping, scaling, rotation, or normalization. One way to make this faster is by using different third-party well-optimized libraries such as OpenCV. But it can be even more beneficial to perform this operation on GPU, especially when ML workload is also performed on GPU, because it eliminates unnecessary data transfer. Normally, it requires writing custom shaders for APIs like OpenGL, Vulkan, or Metal. In our project, we used custom Unity shaders, which allowed us to make pre-processing few times faster. But we should also consider making pre-processing as simple as possible by reducing the number of operations. If, for example, we have input images in the same format as the phone camera provides, then we don't need to do any rotation or format conversion at all. For example, if the camera frame is in YUV, then conversion to RGB can be costly. And in order to prepare the neural network to work in the same format and orientation that the phone provides, we need to train it accordingly. And that means pre-processing of the entire data set. The next hint is specific to real-time image segmentation, when we are dealing with a continuous stream of frames and have a grayscale mask as an output. In this case, we can use an RGBA texture, RGBA input texture, the following way. 3 components RGB are used for the current frame, and the alpha channel can be used for the data from the previous frame or the result from the previous frame. This can help to make the neural network inference produce more precise results, and it also improves stability, because in this case we consider the previous results as well. In this case, we also need to train the neural network accordingly, because we need to have sequences of frames in the dataset. It is also worth trying to improve the quality without affecting the performance too much. For example, there are different tricks that can allow us to make imperfections of the neural network less visible. For example, a clever blending algorithm can hide binary mask imperfections. And also sometimes neural networks that allow us to detect landmarks can produce not very stable results. That means the results can differ very much frame to frame when the actual images are very similar. And in this case, a simple interpolation between frames can help us to improve the results without changing the neural network itself. So we have mentioned different compute units and pipeline optimizations that you can make, but now we would like also to discuss another topic which can be quite important when it comes to optimization, and this is data transfer and synchronization. When we use GPU both for ML and graphics, then it can be beneficial because we can reduce data transfer overhead, and also we can establish efficient workload scheduling. So here you can see the low-level APIs that are normally used by ML frameworks for mobile GPU inference. Normally it is OpenCL or the same low-level APIs that are used for graphics, like for example OpenGLES or Metal. TensorFlow Lite uses OpenCL or OpenGLES on Android and Metal on iOS. But how can we benefit from it? To allow smooth interop between ML and graphics, we need to reuse the same synchronization primitives or data storage objects between two workloads. For example, we can schedule a neural network execution and graphics and frame rendering at the same time. But using a semaphore, we can make sure that the second operation starts only when the first one is finished. And if we are using the same API for both workloads, then we can use it directly. If we use two different APIs, it is still possible by using different API-specific extensions. So let's now summarize the key points that we have discussed today. So machine learning becomes more and more popular in gaming due to use cases such as AR, gameplay, and graphics. And real-time neural network inference support on mobile also becomes wider because we have well-optimized ML frameworks and new lightweight NN models are developed. And also we can definitely see hardware evolution and also new NPUs. When you are working with ML and gaming, you should consider different compute units for your NN model, depending on the task you are trying to solve. And the optimizations and hints we have provided today can help you to achieve better speed, reduce memory footprint and bandwidth, and also reduce power consumption, which is especially important on mobile. We have a number of useful resources to share, and we encourage you to apply these tips in your projects. For example, here you can find links to 2 blogs about the AR Filterup I have mentioned before, and also an in-depth guide to smart pruning. Thanks everyone for attending this talk. I hope it was useful, and see you next time.